In our last section of chapter 4, which is on differentiation, 4.4 talks about L'Hopital's rule and the inverse function theorem. Now, L'Hopital's rule, I imagine you remember from calculus. It essentially says that if you have a function that maybe could be a polynomial over a polynomial, a rational function, or just any differentiable function over any other differentiable function, call it f of x over g of x. If the limit as x goes to some particular value x naught, suppose f, the limit of f is 0 and the limit of g is 0 as x goes to x naught. Well, that doesn't help us too much in computing the derivative, but maybe we could look at the rate or velocity at which they are approaching 0, and that might help us out. So we could look at f prime of x over g prime of x as x goes to x naught, and perhaps that, suppose that has a limit, a value. Well, that's what L'Hopital's rule looks at. So we'll state L'Hopital's rule, do a few examples, and we'll actually prove L'Hopital's rule. Okay, Theorem 4.3, L'Hopital or L'Hopital's rule. Suppose that f and g are continuous functions on the closed bounded interval AB, and they're differentiable on the open interval AB. And let's let x naught be any number in the closed interval from A to B. If the following three conditions hold, the first one being g prime of x is never 0 for x in the closed interval AB, f of x naught and g of x naught are both 0, and if this limit exists, f prime over g prime of x as x goes to x naught. That's the same as f prime of x over g prime of x. If that limit exists, then this limit is right here, the same as this, is equal to the limit as x goes to x naught of f over g of x. So to kind of reiterate, the limit of f of x as x goes to x naught is 0. The limit of g of x as x goes to x naught is 0. So if we want the limit as x goes to x naught of f over g, we can simply obtain, if it exists, the limit of f prime of x over g prime of x as x goes to x naught. Oops, I guess I wrote that wrong. X going to x naught. Well, let's, before we prove it, let's do a rather simple example. We're going to take the limit as x goes to x naught, so x naught is going to be 1 in this case, of x minus 1. So let me just go ahead and say that f of x is x minus 1, and the denominator function will be g of x is radical x squared plus 3, radical x squared plus 3 minus the number 2. Well, as x goes to 1, as you can see on top, we're going to get a 0. And as x goes to 1 on the bottom, we're going to get a 1 plus 3 radical 2 minus 2, which is also a 0. So the limit as x goes to 1 would give us the individual limits of a 0 over 0. So L'Hopital's rule does apply. And by the way, I should have mentioned that both of these functions are continuous and differentiable for all values of x, the entire real line. Okay, well, let's see. Since the limit would be a 0 over 0, let's take the derivative of each function. F prime of x is just the constant function 1. And let me see, this is 1/2 minus 2. So g prime of x, maybe I'll do my scratch work down here, would be 1/2 x squared plus 3 to the negative 1/2 times the derivative of the inside, which is 2x. So that 1/2 and 2 would cancel, and it would give me an x upstairs and a radical x squared plus 3 in the denominator. I think that looks right. So we've got g prime of x equaling x over radical x squared plus 3. So maybe I guess I can keep all of that up. So let's see if this limit exists. The limit as x goes to x naught of f prime of x over g prime of x. So 1 over x over x squared plus 3. That fraction is the denominator. Well, this is equal to the limit as x goes to x naught. This is like the reciprocal of the denominator. So radical x squared plus 3 over x. So x naught is a 1, so I guess I didn't need to write x naught here. I could have written a 1 there, and here as well. So this looks like we're going to get the limit of the numerator as x goes to 1 is radical 4. The bottom is a 1, so we get a 2. So the limit of this from the theorem is 2, which tells us that the original limit is also going to give us a 2. So this is equal to 2.